We are back. Um, we are going to finish up the hatch for version 1, get that released, and then we'll get back into making the changes for the newest version. But 1 second, let me get this shared on the Twitters. All right, now we're back. We are getting the reworked hatch released for the first version. I think I'm going to call this Tough, pTumbler Tough. So we have pTumbler Mini, we have pTumbler this one, which is pTumbler Tough, and then we've got pTumbler CNC, which is going to be the 3D printed slash CNC slash casting version of this, which is going to be the ultimately the cheapest version. I did finish last night building the prototype, and the bad news is you can see it in pieces behind me. I got it working for approximately 30 seconds. And then I did a user ingress test, which is to say I put my hand in there to see if I could hurt myself. Um, and then the motor exploded. So there's good news and bad news. The good news is the flexure we FEA'd was not the weakest link. The flexure did swimmingly. The problem is that the $15 motor we're using is made out of something pretending to be steel, which meant one of the gears inside exploded. So we're going to have to work on speccing a better motor today, which is going to drive a redesign of most of the two newest versions of the assembly, which is a bummer. The good news is this one still works. So we just want to get this cleaned up a bit and fix that hatch. Get these parts released, and then we'll go back and start a not a redesign, but an implementation of an updated motor. I wish we could use this motor. This one is done pretty well, but it is not sold at the speed we need. Essentially, we need a much faster motor for this to work, and this is only I think 10 RPM. So, or no, I would say it's actually too fast. I think that was the problem. Anyways, long story short, we can't get this motor that has been working on the first version in the speed we need. We'll go back and reinvestigate. Maybe it's just because the vendor I'm using doesn't have it available. Maybe it is sold somewhere, so we'll go look for that. So yeah, that's what we have on the docket today. So we'll get through this list for the implementation of the prototype. So I had a shower thought today about my approach to failing quickly here. Um, so software engineers know this. They know that if you want to build something complex, you have to build something really quickly and just it's going to be buggy, and you essentially compile and run the thing as frequently as possible. And that works for them because there's no capital involved with running a program on their computer. You could argue that the machine learning folk have a little bit more capex involved, especially if you're training large models, but I think they train at some smaller scale that enables them to do that. Anyways, the thinking though, the thing I want to point out is for hardware, you can't do that. We don't have that luxury. We have long lead times. So today we have send cut send, which, you know, in Proto Labs and Xometry, so I can get parts in within a week, which is fantastic, but that's still a week. Imagine if every time a software engineer wanted to try something in their code, they had to wait a week to compile. Doesn't really work that way in the real world. So we don't get to do that. To make matters even worse, it costs money. So those parts cost money, and they cost even more money the faster you try to get the parts made. So when people talk about failing fast, when you're talking about hardware, it often means you're failing fast and failing expensively. So it's a pretty cool time to be alive, where we have assets like on-demand manufacturing that enable us to truly fail fast. Rant over. um, Actually, it's almost over. I have one thing to say. Think about the companies that build hardware that aren't doing well, and you will find that they do not fail fast. That is very, very important. And you'll notice this if you start looking at companies. Let me make sure this isn't gonna start making a bunch of noise. 1 second. If you start looking at, yeah, 10 RPM is too fast. It's funny. I actually did the math on this, and I don't have it in front of me. Actually, I do. 1 second. If you want to know, there's actually a way to find out what the optimal RPM is. This is actually really cool. I pulled out my physics book and tried to figure out what the optimal RPM is. Because there is an optimal RPM, believe this or not. So, yeah, let me draw this out real quick. This is actually kind of fun. So the problem is if you spin the barrel at, say, let's see, isolate just the stuff we care about. Um, if you spin this barrel with the hatch, all right, let's say you put the media and the parts in there, and you spin the barrel at, say, 1,000 RPM. The material clings to the sides, and then it doesn't tumble. It's the opposite of tumbling. It's just a spinner, which, it's a centrifugal spinny McDoodad, which isn't particularly useful. So you have your media in here, right? You spin this at 1,000 RPM, and when you get to the top, it's stuck. So you actually don't get anything. And so there are tumblers that get around this. They have rotary tumblers. No, not this one. What is it called? Ben Krasnow just did this. And he gets around it by, I think it's called, what's it called? Centrifugal tumbler? That's so annoying. I remember just seeing this. He's got it on his GitHub. Let's get the most latest ones. Planetary. It's called a ball mill. So the way, this is a fantastic video, by the way. If you haven't seen this applied science video on, um, I think he was creating some exotic material, some iron oxide, I think, that was semi-magnetic. Anyways, part of the process of doing that was he had to take, I think it was aluminum oxide, tumble it with iron. I can't remember the materials, but long story short, he had to tumble at an extremely quick rate materials inside of a tumbler. But the problem is, because of this problem of if you spin the tumbler too fast, it actually just sticks to the barrel. Um, the way to get around that is, well, you just create your own version of gravity. And you do that through um, the centrifugal force, which isn't real, but bear with me. Um, so you just spin it super quickly. You match the RPMs of the tumbler to the RPMs of the mechanism that actually spins the tumbler itself, and you get to make artificial gravity. Um, and then you end up just accelerating as quickly as you can spin the thing, the actual tumbling and crushing effect. And it was super effective actually. And I might actually, after I finish the standard rotary tumbler, try to take apart his design here and do a fork. Try to make a mass manufacturable version of this. So, anyways, long story. What I'm trying to say is you're limited by gravity because if you spin too quickly, you get this case where all of your media and parts just stick to the barrel on the outside. So there's an actual theoretical maximum where you don't do this, right? And so the answer to that is, what is the maximum speed you can rotate this and not have the centrifugal force overcome the force of gravity? So you have force of gravity, and then you've got the centrifugal force. And once they're equal to zero, in other words, when F sub c is equal to F sub g, you're in equilibrium. So then you can say, okay, well, if at some RPM I get this, then all I have to do is bring my RPM slightly down, and that's my optimal speed. And so I derived this from, I'll write the equations, and I'm not going to do the derivation, but I'll just write the equations, and then I'll let you go figure it out. And if you can't figure it out, just send me a message or tweet me, and I will clean up and show the derivations. But essentially, you end up with an F sub c and F sub g in the free body diagram. I'll draw it here. In the free body diagram, you have your center of mass, and it's at some distance r from the center. And your free body diagram looks like F sub c and then F sub g, and then that equation over here looks like, let's see, um, it's so F equals ma. Well, actually, first let's just write these out. So F sub g is F equals ma. So that's literally mass times acceleration. And then we get F equals ma for this one as well. And you get m, but then a is, because this is a polar coordinate system and you're rotating around a center point, essentially a in sub c is equal to v squared over r. And so when you sub that in here, you get v squared over r. And so this is your governing equation for equilibrium. In other words, this is saying your force of gravity is equal to your centrifugal force. And again, centrifugal force is kind of a misnomer here, but just trust me. Anyways, you solve for that, and what you get is, I think, omega is equal to the square root of my freeform's bugged out, so I can't actually get the answer. We're gonna have to derive it real quick. 1 second. So when you do some actually, let's just derive this. So your m's cancel out. And so you get v squared over r is equal to acceleration Um, and we want v squared over r to be equal to omega. And I think omega is, isn't it r theta? No, r v? Yeah, that's right. So this is equation 1. This is equation 2. We sub 2 into 1. First, we derive this in terms of angular speed is equal to velocity. So here's your equation 2. Here is your equation 1. And so now we get, once we plug in v into equation 1, you get to solve for and find your maximum angular velocity. And so v squared over r turns into omega over r squared over r, which is equal to acceleration. Is that right? Oh no, wait. We actually don't kill mass here. I think we leave mass alone, right? Yeah, because mass times acceleration is our force, which we already have an answer for. So I'll put the m back. So it's mv is equal to force gravity. Or it's actually, force of gravity is just weight. And keep in mind, omega is not the same as weight. But because it's going to be hard to see because we're streaming here, I'm just going to leave this as force gravity. But this is roughly weight. Okay. So this turns into this. And now we will solve, and then I think we get m omega squared is equal to r cubed. Yeah, m omega squared over r cubed is equal to force of gravity. I think this is right. And then we solve for this. Yeah. So this is going to help dictate what that maximum speed is going to be. So let's check our work real quick. Oh, I think I might have messed this up. Yeah, I got this backwards. Let me fix this. So omega is actually, what is omega? I think I have it reversed. V is equal to R omega. V, yeah, I had this backwards. Whoops. Okay, now this is right. Now we solve. So this turns into, we sub 2 into 1. I'm gonna start, I'm drawing on a mouse, so this is tough. So sub 2 and 1, and we get m times r omega squared. Now this is starting to look cleaner. Is equal to Fg, or weight. And then now we can solve this. So it's m r squared omega squared over r is equal to f sub g. And now we cancel out. We get m omega squared r. Yeah, because the exponent of 2 goes to 1, and that's equal to f sub g. And now we solve, and we get, we move these two over, and we take the square root. So omega is equal to the weight. Yeah, the weight divided by the mass times r. So this is our equation that governs. And so what this tells you is this is the maximum angular speed you can obtain your um, before your pTumbler doesn't do its job anymore. And that is very relevant. Um, so we could actually go figure this out right now, and we might want to do that because we are going to have to respec the motor, and it would actually be good to know what our target RPM is, driven by requirements of getting maximum tumblage versus just doing torque checks. We've just been guessing essentially the maximum speed we need. And I wonder, has anyone actually done this math before? Let's find out. AI is going to answer. Wow, this is totally useless. Yeah. Okay. So what do we know here? This is so essentially we want this number. Actually, we don't know what this number should do. We don't know if we want it to rotate faster or slower. I guess we want it to. Actually, no, we're just going to get an answer here. So we can play around with these variables to understand what's going on. So let's rewrite this into a more sort of clear way of looking at this so we can think about it. So square root is the same as an exponent of 1 over 2. So we have the weight, and I'm actually going to write that out. Which is FG, F sub G. And then we have mass times radius. And so what happens to the critical speed if we increase the weight? The critical speed goes up. So that's saying the more weight you add, the faster you have to spin to have the mass stick to the walls of the tumbler. Now think about that. Think about that. Like use your brain's eye, and do the mental experiment. Like you've got a pTumbler in front of you, you start spinning it pretty slowly, and it just keeps tumbling, and then you go faster and faster and faster, and then it starts to stick to the walls. Now bring it down a little bit, and now it's actually tumbling again. Now imagine you put more mass in there. Let's say you drop a heavy rock in there, and you go back to the same speed where it started to stick to the walls. Does your intuition say that it's going to stick to the walls, or is it going to continue to tumble? My intuition is agreeing with this equation. I think it does continue to tumble because that roughly makes sense because you have more energy. It takes more energy to get that mass to stick to the walls. Or yeah, I think that's right. So far this is agreeing with my intuition. Um, oh, I'm seeing something wrong here. I think that hmm, do we set this equal to something? F sub g. We had ma. Hmm. I think the ma cancels out there. I think it did this wrong again. So this is actually ma. Then these cancel out. And so then we get acceleration over r. So it's independent of mass. But what's acceleration? Isn't it w squared over r? Can't remember. Delta omega over delta t. But there's a way that you can write this without calculus. I think it's w squared. Or it's also alpha over r. Yes, it is delta. I don't want to do it in terms of delta omega. I think I can't remember what it is. I never think in terms of polar coordinates, so this is something I have to dig up. I think this is a ChatGPT question. Oh, of course it needs time. Duh. That's how we get our MA. Um, wonder what it was. Oh, duh. This isn't A, it's G. If you ever want to publicly humiliate yourself, I have a really cheap way to do it. It's stream yourself doing engineering. Guaranteed to work. Okay, so I was confusing myself there with A. A is really G, which is just the acceleration of gravity. So we're fine. And so all of this, I'm going to get rid of my FGs here. I should never have done FG. That really confused me. It's M times G. That lets your M cancel out, and then it lets you get this. That makes sense. Now this makes sense. And this is why the ball mills work so well. It's because your G, you can actually just make bigger by just spinning it faster and faster and faster. So now we have our answer. And this is really simple. So we're essentially saying you can't change gravity, right? At least in the current design. Um, R, R is the only thing we can change. And so interestingly, we can actually now start to think about what happens to the speed required to make this thing stick to the wall. And the answer is it's essentially gravity divided by R, the square root of that. So if you make your R, if you increase the diameter of the barrel, right? If you make it bigger, um, the speed goes down, right? We'll go test this in Python, but the speed goes down because the denominator um, gets bigger and then you're dividing by a larger number, and so your speed goes down. But if you make your R really small, that means your angular speed can go way higher, which kind of breaks my intuition a little bit. Hmm. Let's actually do this. Let's write this out and play with it. So uh, ChatGPT giving me the latex for this. I wonder if it'll give me the Python code for it too. Okay, I like AI a lot more now. That's fantastic. That is fantastic. If it works. Markdown. So here's an interesting thought or fact, not thought. The speed at which you take material away from your parts is the speed at which you do effectively the tumbling. So in other words, to have a quote unquote finished part, um, to have a finished part, it takes energy to erode away the surface of the part, right? And so essentially you want to find what's the fastest way to get the most energy into the part to give you the finished part. So it's really an energy problem. Kinetic energy is 1/2 mv squared. In other words, it squares with velocity. So you can put way more energy into the system by just making it spin faster. So what the critical speed does is it tells you what's the fastest you can spin before the system stops tumbling. Thinking back to what speed we actually want the speed to be as fast as possible, which is the critical speed. So what we want, ideally, is a way to get the tumbler to just before the critical speed. Then we're imparting the most energy into the parts, and we are not switching over into the critical zone of adhering the parts to the barrel. So that is the engineering reasoning behind what we're doing here. And I will write that out real quick before we get the answers. Okay, here is our LaTeX. Is it pronounced LaTeX or latex? I'm not an academic, so I don't actually know. I just use it. LaTeX, yeah, that's it. Okay. We have our equation. Let's copy ChatGPT's answer. I bet you the math function isn't called and this is going to error. Surprise. But I do have NumPy installed. Okay, great. Um, uh, and then we'll adjust it for RPM because we actually care about RPM. Did we use omega here? Yeah. So omega, here we go. Man, if you're going to rag on AI coding, come speak to me first. Because as a math layman, I mean, as a math not layman, but a code layman, I'm really enjoying it. 20 RPM, look at that. You'll love to see it. Actually, these are made up numbers, so never mind. We're actually at 0.1. I think so, yeah. So our radius is, let's see, 100 millimeters, and that is 0.1 meters. So yeah, 0.1. So 100 RPM. Well, I'll tell you what, we're not spinning this thing at 100 RPM. We're not going to create an, a small scale energy weapon in a garage. That sounds terrible. So we're not going to do that. It sounds like a lot of energy, and we should not do that. Actually, can you get rotational energy without mass? I think no. I think you need it. I squared. Okay, we're not going to go calculate this, but it's a fun little experiment. Okay. It's very fun to find out. See, this is why you do the derivation. Because now we know mass doesn't matter. That's really interesting. That would surprise me. Okay. Anyways, so now we know our maximum. It's 100 RPM. The faster we go, the better. But let's leave it at, yeah, let's leave it at that. What I'm curious though, how much is 100 RPM RPS? How many rotations per second is that? It's divided by 60, right? So in other words, you're within 0, 1, you're actually doing 0, 1. No, 0, 1. Yeah, that's scary. We're not doing that. We're not doing that. Maybe, no, we're not doing that. All right. Okay, so now we know our maximum speed. That's useful. We're not going to go this fast. What we are going to do, though, is get back to design. Okay. So let's get back to design. I'm going to prioritize the list. Actually, before I do that, let's go release this real quick for version 1. This version of the design. So where are we? think it's a good time to pull a timestamp on this. What revision are we at? Well, that's getting unruly. Okay. We'll go back to the naming scheme I came up with later. I guess we could do dates, but I'm too lazy to do dates. So we'll just go to using lettering schemes. Okay. You were close. 70 RPM was, let's see, that was, you were off by, actually, you were off by 30%, which for a wild ass guess is actually pretty impressive. So you get a gold star, whatever the equivalent of that is for an engineer. Okay, let's get this going. So we had the design over here. So all we have to do, I think we've tuned up the design. We just have to add this portion of it. So we don't have this overhang, which is going to help define the curve of the barrel. Ooh, that's wrong. That should be flush. That should be flush. How do we determine how to make that flush? It also has to be symmetric. All right, let's edit that real quick. Make a midplane, slice it. It's going to be symmetrical. Then we are going to pull this surface up. And we're going to subtract via Boolean the barrel. Get that backwards. Then we're going to save the barrel. We're not going to have it removed. That should be good. Did that work? Did not work. Why didn't you work? I think the slice works. I'll just do that. I forgot that they added slice, so we should be taking advantage of that more. I'm sorry, they didn't add slice. They added the ability to slice curved surfaces, which has been one of the best things to happen to me this year. Okay, so this is actually a curve. You can't see it. If I dimension it, maybe you can see it. Okay, this is kind of annoying. Anyways, we're going to just ensure that this actually is straight. Why is that? No, it's not. There we go. It is, yeah, how did that end up straight? No, never mind. It's just an illusion. So I'm going to subtract this to get it to be, yeah, flat. It's not a big deal, but I have a suspicion that it's going to break the intake engine if we're not careful. So this should be 90 degrees now. Yep, 90. Perfect. Okay. So we have to add that feature. Yeah, Lex, that's right. That's why we just fixed it. So I drew that sketch to make that line straight. So as long as that was a Boolean, subtract, yeah, we're fine. Well, let's double check. If I project this face, it should be one single line. And it is, so we're good. And we're now at a point where I'm going to clear history because this is starting to get unruly. And we're going to start adding the detail here that I was talking about. Let's isolate the barrel. So I'm going to slice this in half to work on it. And then we'll mirror it back over when we're ready. So first things first, let's get rid of this radius, and then we will pull that section back to look at the geometry. We're going to get rid of this radius. We're going to carry this out. So I don't know what this distance is going to be yet, but I'm just going to pull it out of the way for now, just to get a good look at it. So we probably want like an inch of material that's going to connect the top and bottom here. Actually, I might just leave this open so it's easier to see what I'm doing. So we're working on this section right now. So this little sliver of material I talked earlier about me being worried about. So we're going to model that. And actually, I think we have some room in Z here that I wasn't accounting for, so it's not going to look as goofy as this. But we'll see. So what is this distance? 10. So a little bit less than a half an inch. Not the end of the world, but I would like more. So let's get that up to an actual half an inch. So this distance is currently 10.6. So we'll get that. Just add 2 to that. So now we're at about 12.7, which is about half an inch. Yep, 12.6, which is good. We're not breaking edge rule here either for now. So now we can, what can we do? Let's actually get this, let's get a surface off of this, which is going to be roughly that 12 inches. And we'll slice this body and we'll extrude it out. Yeah, just do this in ISO. So now we want this distance to be probably an inch. I think we're at 8, so we'll want another 17. So the distance from here to here should be 25. About 25, yep. All right, already seeing a problem. This screw is in the way. Huh. So when we extend this over, I'll show you what I'm talking about. You won't actually be able to get a socket, a hex wrench in here to actually turn the screw. So I think the way we can fix this is to flip this detail. I have the nut on the outside. which I don't love. Which I don't love. But we do what we must. So I'm just going to mirror this geometry over. Why are you not able to? I'm slicing, that's why. Okay. So there is our nut detail. Do I have my nut in there? Yeah. Actually, we don't want this either. So I'm going to mirror this over. Probably wondering what the hell I'm doing right now, but it's all right. So we're going to have to pull this down a bit. So let's fix this up. The parametric mind cannot comprehend. So we just did 5 there. I think 5's all right. We're going to pull these surfaces down. That is not working. Knew that was going to work. I think it's a simple kernel thing. I think I can trick this. I'm going to trick the kernel. There we go. It's really all engineering is. It's just tricking the kernel. All right, and so now we're going to pull this down. I think it was 5 we said earlier. That looks about right. Hardware is about right. Probably need a little bit more. That's too much. We're just going to need a longer screw, I'm afraid. Actually, this is fine. This is fine. This is actually good. This is actually good. We don't actually need to bite into the material at all on the screw side, I think. So we're just going to clear this out for the screw. It's starting to look a little goofy, but I think we're going to be okay. Actually, I do want to save that geometry. I'm just going to clean this up. Okay. I think that's what we want. Am I not... I might not be thinking about this correctly. Am I thinking about this correctly? I guess you can get a hex key in there, so that works, but this is kind of hideous. This is kind of hideous. So it has to be long. This is not my proudest work. All right, so we have to add, essentially this doesn't work right now because you can't actually get this screw in. When you try to get it in, you hit this face right here. So you actually interfere. So we actually need to pull this out a little bit more, which means we have to add more material down here, which I guess we can do, but I'm starting to not love this. And it's particularly annoying because you need to have exactly this length of screw or else it doesn't work. And that screw right now is 15. And I think I bought 16 millimeters. So we should really, oh, that's not right. Should get that to what it's actually going to be. Yeah, so now it's 16. That's actually right. So let's get this down. Why don't I just do it in the other way? Because I'd rather have a bunch of ugly protrusion here on the inside of the barrel than on the outside. That's why. So now this has to move down 5. So now we should be able to get this screw in and out. Yes, just barely, but yes. I think you might be right though. I don't know that this distance is actually that much smaller. That's 25 and this is probably going to be 25. 30. It's a little bit bigger. So I guess I was right, but still don't love it. All right. Good is good enough. So we need this to rotate. I think we have 75 degrees, and so we need to cut out this material. It's starting to look a little flimsy. Can we move that away to give ourselves more room? Yes, actually, we can do that. Sorry for the dog. I think we're breaking edge distance rules here. But I want to get more detail in here before I start worrying about that. Actually, I'm breaking more than just that. Because of this, we can't actually have this tie into that. Hmm. I guess we could stack this like that. I don't think this is going to work. I think we're colliding here. Ugh. So what the hell do we do? It's very annoying. We are designing a pTumbler, Rich. I don't know what's going to happen here. We could slide it in from one side. Then we'd have a gap here. But then you'd be able to get media out, which isn't good. And I don't want to change this part to account for that gap. So that's probably not going to work. Actually, if we move this over here, this still works. No, it doesn't, because now this is free to float. So we actually need this screw on this side. So that doesn't work. All right, let's undo this and take a step back. Okay, so here's the situation. This sketch works on the other side, but it doesn't work on this side because we have this spring plunger that we have to retain in place correctly. And it doesn't work because the idea is you're supposed to be able to rotate this sheet metal into this guide here, but you can't because the spring plunger retainer gets in the way. This is what you might call a skill issue. So we have to skill ourselves out of this. And I'm not redesigning the spring plunger. I'm not redesigning anything except for this stupid hatch. So the constraint here is we can only modify the hatch design. We're not going to come in and redesign this part because I've already made it, and we should be able to outthink this problem. And I'm out of ideas, so yeah, the inside opening is how you do it. And if you want context for why we're doing this, because the prototype that we did came back and the barrel works. This, that's nice. But the hatch is a disaster. And so you can kind of see what we're doing in CAD right now. It's actually that detail. We're going to flip that. But what we're doing is we're trying to find a way to get this hatch such that this hatch such that you can actually just slide this piece into the guide, and that will define the shape. Right now, the shape is not well defined, and that's a problem. So we're trying to get that fixed. Good news otherwise. I mean, it does work pretty well. I'm pretty pleased with this kind of skeleton and wrap construction. It's going to be louder than hell, though, but it works. Anyways, that's the problem I'm trying to solve. Okay. All right. All right. What are we gonna do? Whoa, why are you making noise? There we go. Okay, so we could slide it in from the side orthogonal to the original side, but again, we run into this gap issue over here, and we don't want to redesign that. We can't move the spring plunger. That has to stay where it is, so we're pretty much locked into this position here. In Z, Z being left and right, which is actually Y in the model coordinate system. So, all right, let's assume we can make this work, and let's start to think about what we can do for the spring plunger. Oh, duh. I got it. Okay. We split the spring plunger tab. Yeah, why didn't I think of this? And we just attach that to the top here. So it literally looks like this. All right. Man, I took my stupid pills this morning. Okay, there we go. And so now that's going to attach here. What a relief. I thought that was going to be a showstopper. All right. So now there we go. Problem solved. Crisis averted. And this, we should be able to just pull that out of the way. And that is the part. Let's clean this up first. Okay, so now it's working. We have to make it less ugly, among other things. So we just did that protrusion check, and this hardware is a little too close, and we're breaking edge distance rules here. So let's fix that first. Just going to rotate this over 5. See if that works for us. I want to get this whole 2. And then we're going to pull this back to get us, yeah, guess what we're looking for there. And actually, I'm just going to rotate this face because there's no need to make it too complicated. Okay. Getting awfully close to minimum material condition down here, but actually this part's hideous. So let's, I mean, this is the ugliest part I've ever designed. So let's get the let's actually get the required cutout, and then we'll come in and start to fix this so it looks less hideous. Remember, if a part is aesthetically displeasing, it is incorrect, and it is your job as an engineer to find out why it's ugly. If it's ugly, it's wrong. Period. And if you disagree, this was a nearly championship winning race car, and every single surface served a purpose. So functional is pretty. And to prove the point, the car that beat it that year, I believe, was even prettier. Was it really this one? Kimmy won in this one, I think. Yeah, it's even prettier, so I'm right. We're all right. We all knew that intuitively. I think it lost. They also cheated to design this car, so unrelated. Anyways, so pretty is good, and this is not pretty. So let's make it pretty. So I'm being facetious. The real reason why pretty is good is because every design, every surface on your part should have a reason for it. And engineers can tell, yep, like that's what we're going to do. Yep. That was fast. Did you just go and draw this real time? Trying to take my job, man? Come on. It's crazy. Yeah, so every surface, every contour of your part should have a purpose. And the answer can be, the purpose could be, it's cheap. That's fine. It's cheap is an answer. But even it's cheap looks good. Actually, we're going to need the context of the assembly to really rotate this correctly. Because I think it, nope, that's wrong. That's wrong. Find the part. So, oh, can't snap. Turn off the frame. I think it was 70 or 60. Yeah, 60. So essentially we have to be able to handle 60 degrees of rotation. So you can open the hatch. So let's subtract these two bodies. We'll keep the original. This is my way of cheating through interference checks for parts, essentially. So if you make this cutout, and then you rotate this part 60 degrees, it'll sit perfectly right there. No, we're just going to copy that design, Lex. That's the design we're going to go with. All right, so let's make this hideous part less hideous. So actually, let me draw real quick what I know is wrong about this part. So the way I think about this stuff is I try to think about where the load is. And so these are the load carrying surfaces. This is where the frustum of the bolt is going to carry load. I know that this surface here is going to carry load because that is going to get transmitted through the screw head over here. And it's going to go this way. And then this surface here is also going to carry a tiny little bit of load, but not very much. And then finally, same story, the frustum of these bolts. It's going to do, well, the nut there is going to do that. And then you roughly along this surface get some load. So what this is telling me is that I actually don't need a lot of material here because there's nothing reacting the load on this side. I also know that I don't have anything reacting load over here. So I can take material away from there. I don't have a lot of material, I don't have any load really going through here because there's nothing reacting that. But it's going to add costs to cut that surface. So what we might do is instead of doing lightning holes like this, what we'll do is we'll probably just come in like this, pick this back up, add a radius there, and then actually this contour here can probably look something like this. This should make our part look less ugly, in theory. Actually, this one is probably going to look more like this. So yeah, I think in terms of loads and where they're going to go. And also I forgot to say this is going to carry load. So, and that load path is essentially from here to here, and then from here to the contour that follows the sheet metal part. Okay. I'm afraid we're breaking edge distance rules here. So let's take a step back. Double check that we're not. Taking away a material that we, well, let's make sure that we can add some material back, because I would like to if we can. So good news, we can, and it follows that curve right here. This curve. So we'll start there. I believe that's this curve. Yeah. Although it doesn't appear to be center, so we'll just do one of these. Okay. So we'll get rid of that edge. We'll add some material back over here. Delete the surface. And just as a sanity check, let's rotate this to see if we have an issue. And I'm going to clear history here in a second. Yep, looks good. Great. All right, let's take a timestamp. And then clear history. Okay, so we actually want to offset the surface slightly because we want a little clearance for essentially ensuring that we don't collide with the barrel surface prematurely. So we'll add a little bit of clearance there. That should probably be 0.5 millimeter, just to be sure. And then we'll come in and start to think about what this surface is going to do on the inside. So we can just say, all right, we want 10 millimeters all around. That's too much. So let's go to 7. Okay. And then actually simplify this. We'll do a single edge offset. Actually, I can't do a single edge. So we'll do the loop. We'll do, see if we can get all of these. Okay, so this is going to define my, my minimum edge distance to this hardware here. And so we're just going to draw a straight line through that, I think. And as a matter of fact, I think we'll draw it from this curve. Make a tangent. First I'll lock this. Okay. There we go. Looks a little too close. A better way to do this. It'll be fine. Okay. Down here, let's fix this. Make this tangent and perpendicular to this edge. I'll add that material back. I can do CAD with a third of my screen because I've been I've been broken as a human, and when you engineer at a large organization, you spend most of your day staring at spreadsheets and email. So, or Slack now these days. And so I'm pretty much used to this. So I'll usually have email or Slack open on one side. But actually, now that I know about how to use properly multiple virtual desktops, I've been abusing that, and it's been less painful. So I'll have this cut relief. There's still something's irking me about this. Why is that irking me? That's why. Better fix that. And this is lagging for some reason, so I'm going to fix that. Let me restart this real quick. That's why. Those edges weren't concentric. 2.32. This is 2.3. So we'll just rotate them both 2.3. Actually, that's not going to work. All right. It's going to brute force this. So much of my life these days is just brute forcing CAD. Okay. Yeah, that's right. Oh, that's driving me nuts. Why is that? Okay. Now we're going to have that cut and relief. Wait, why did we need this space again? Yeah, I think my thinking on that was incorrect. No, I think it might be right. We're just typing for space over here, so it's just going to look real weird, but I don't have a better option. Okay. So what are we doing over here? I think we actually need a little bit more space here. Okay. So we'll increase this diameter again, or reduce it. And then we're gonna, all right, that looks better. And now we're gonna draw the contour to, well, this edge distance here is gonna drive, so we should really set it equal to that. It's 9. And so this from here to here is more than 9. It's 13, so we need to pull this back 4. Okay, that looks better. So now we can come back and draw these features here. So we'll just project this, and then we'll say, well, let's just do an offset of the roughly 10 that we talked about. It's 9 really, but we'll do 10 here. So we're going to want a curve that does this, and we're going to want a curve that does this. So we want this to be 10 roughly away from here. Let me fix these. Okay. Movie tangent, delete this, and then we're going to set this roughly equal to, really this can be coincident with this. How do we do that? Offset this 10. Okay. We have a little bit more to pull in here actually. We want to pull in the, yeah, this one. And we'll make that tangent. And then this distance, how do we set this? Could just do that. Why not? And then here, we do another tangent. There. Okay. And then here, so I don't have a good way of doing this one, so I'm just going to kind of make it up. I know 10's roughly the dimension we're going for, and then these, I guess we can't make them tangent, so I guess we can join them. No. And then we set them somewhere in the middle. This is not particularly pretty, but maybe we make them tangent to the surface. There we go. There we go. Okay, that feels better. What is that doing for us? No, that looks like it's not going to work. Honestly, I don't want to spend too much time on this. That's fine. Wait. Okay, now I know what I did wrong. I constrained these incorrectly. I should flip them. This should be 10 away from here. Let me do it for this one. And that doesn't look much better. Make these construction, and then we'll figure this out. Do the same for this side. Hmm. All right, good enough. All right, this looks insane, but I think it's going to get us what we need. We got to get this one fixed. Okay. Now we can fix this. This should look better. I only pulled that section. Okay, now we're going to subtract the weight reduction features. We'll clean this up. Okay, that should be good. Now, I'm a little worried about this cantilever because it's not going to actually, it's not going to define this curve after this. But you could argue that the screw is going to do that. Actually, we should extend this over. Oh, and we actually have to extend this out over here as well. But before we do that, let's take a look at this. We've done a lot here, so I'm actually going to remove parameters. Okay. What are we doing here? I think this is going to be all right, but we don't need this cut out anymore. What are we missing? All right, let's pull this surface back like we talked about. And I think this has to sit just before this curve so it doesn't intersect with this. And we'll double check that in a second. I think we can leave it like that. Want to add a little clearance there. Give it 100 microns. Add a radius. Okay. We should also gap. We should also gap. I mean, not gap. We should also add clearance to the essentially the sheet and the sheet in this guide, and I'll show you why. Because if we do 30 thou stainless. I think it's plus or minus like 130 thou. Or not 130 thou. Yeah, 130 thou. Or 100 thou. Let's look. So advertise, blah, 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 tolerance. It's actually, oh, it's only 2 thou. It's tiny. Isn't that bad? So essentially it's saying on the positive side, it could be 0.32 thick. So we'll want to offset this by, let's just call it 5 thou because it's going to be all over the place. We don't want it to bind when we slide it in, so we'll get 5 thou instead, which is 130 microns. In case you were curious. I'm sure you weren't. Oh, we should add a radius here too. So we'll take away our 130 thou. Did that work? It did. Great. So we'll do 130 thou on these two. This is such a long cantilever. I actually don't think we need 130 thou, but let's go in a little too loose, and we'll see in the prototype if we made a mistake for doing that. So the distance between these two should be, let's suppress, let's just make sure. Yeah, that worked. That's good. Okay. So now we have our gap. I wanted to also extend these a little wide on the sides so we actually sort of collide with the barrel there. So we'll give that 2 millimeters. That will carry over. That will carry over to the other side. Okay, let's do a sanity check real quick to make sure we didn't miss anything. So I'll pull a section from here. So we're looking good on interference with this surface. Screw looks like it'll work there. Do we have a gap here? We do. Appropriate clearances. Oh. I don't know that we can get this screw in. It's the same issue I warned about earlier. Yeah. So that doesn't work. We have to take away 5 millimeters on that. 75, so make that 69, I think. Yep. Didn't work. Oh, it did work. What's going on? Can I just do a move face on this? Ha. No. Maybe if I take this one too. Don't know why that's not wanting to carry over. Okay. So now we should be able to get this screw out. Oof, still too close. I'm going to say, uh, yeah, say we need a little bit more room. That's plenty. All right, let's continue through with our check. It's going to be a pain to install this screw if you forget. So you got to be clear to say that you got to assemble the hatch before you install it. You can't assemble this sheet metal into the hatch skeleton after the fact. There's our gap. Then we should have a nut on the other side. Yep. Okay. Last check. Let's do an interference check. The hatch opening. Looks good. And then we'll check in the context of the assembly. Ooh, we should have checked this as well. So let's open up our hatch. Well, actually, that lining feature ended up saving us having to find out that it wouldn't have been able to close if we hadn't added it. So that is a case of us getting lucky. So that's good. All right, I think it's ready to mirror over. So we'll pull in all the hardware and everything. What's this? That was an artifact. Actually, no, it wasn't an artifact. Do we want that? I think we want that. Yeah, we want that. And let's add, I guess we just put don't actually need. Yeah, we will need. We will need cutting relief because the end mill size is too big to fit in here. Okay. Now I think we can mirror this. Let's do this first. We'll do hardware. We'll do this body. And Boolean, and I think we're done. Oh, we have to do this one too. I think we said we agreed we're going to make this look, we were going to make this asymmetrical and just eat the part cost. So we'll do that now. Why are you doing this? Because you're not actually tangent. It's very annoying. Okay. This is going to be a little flimsy. Like I can walk up to this and just pull it left and right, and it's going to be just free and cantilevered. Because it's so thin, it's only a 1.6 millimeters. I'm a little worried about that. But it is going to be friction coupled to the surface. So it doesn't matter. Don't think it matters. This edge distance does, though. It'll be fine. Okay, last sanity check, and then we're going to release this. Okay. Let's check it from the other side as well. Nothing looks off. All right, ready to go. Okay. That's it from me today. I might just go and release this anyways, off stream, but yeah, I think that's it for today. I'll see you next time.